Hello, this is Janet and Rabia.
Welcome to Everest Physics Academy. In this exercise, we are going to determine the initial position vector and the initial velocity vector of a box dropped from a helicopter. Determine the expressions of the velocity and the position vectors of the box. Determine the equation of the trajectory of the box. Calculate the time of flight of the box and the horizontal distance traveled on the ground. And determine the position of the box when its speed becomes 25 meters per second.
A box is released at time zero from a helicopter 100 meters above ground with a horizontal velocity of magnitude 20 meters per second. Look at the figure. Take the launch point O as the origin of coordinates in the vertical XY plane. Number 1. Determine the initial position vector and the initial velocity vector of the box in the XY plane. Look at the figure. At time zero, the box is at the origin O of coordinates. Then x0 equals 0 and y0 equals 0. Therefore, the initial position vector is 0. Let's move to the initial velocity. Again, look at the figure. The initial velocity is directed in the positive x direction. Then v0 equals v0i. And V0 is positive. Replace V0 by 20 meters per second. You will get V0 equals 20I, and it is expressed in meters per second.
Number 2. Determine the expression of the velocity vector at time t. To determine the velocity vector, we have to apply Newton's second law in order to determine the acceleration, and then we can determine the expression of the velocity vector. The system is the box. The only force acting on the box is its weight, since we neglect a resistance. Then applying Newton's second law, the net force equals the mass times the acceleration of the box. Therefore, mg equals ma. M cancels m. Then the acceleration becomes equal to the gravitational acceleration. But y is oriented positively upward and g is directed vertically downward. Therefore, relative to this y-axis, g equals minus tan j. Therefore, a equals minus tan j in meters per second squared. Now we are ready to determine the expression of the velocity. V equals the antiderivative of the acceleration vector with respect to time. If y equals the antiderivative of b dt, where b is a constant, then y equals bt plus y0. But a, or minus 10, is similar to b. Therefore, the antiderivative of a with respect to time becomes minus 10 tj plus v of 0. But v of 0 equals 20i, proved before. Therefore, the expression of the velocity of the box becomes 20i minus 10tj in SI units.
Let's move to part 3. Determine the expression of the position vector and then write the parametric equations. The position vector is the antiderivative or the integral of the velocity vector with respect to time. Let me remind you with two simple rules of the antiderivative. If y is the antiderivative of b with respect to time and b is constant, then y equals bt plus y0. If y is the antiderivative of bt with respect to time and b is constant, then y equals bt squared over 2 plus y0. Now, let's take the antiderivative of the velocity vector. Let's start with the x component. The x component is constant. It is similar to b. Then, the antiderivative of the x component with respect to time is 20ti. Now let's move to the y component. The y component is variable. It is similar to bt. Then the antiderivative of the y component is minus 10 times t squared over 2j. And here we have r0. But r0 is 0. Then The position vector of the box is 20ti minus 5t squared j, and it is expressed in SI units. Now let's write the parametric equations. X equals 20t and y equals minus 5t squared.
Focus, please. This is important.
Number 4. Determine the equation of the trajectory. As you know, the equation of the trajectory is a relation between y and x independent of the time t. X equals 20t, then t equals x over 20. So replace t by x over 20 in the expression of y. We get a relation between y and x independent of the time t. So y becomes minus 1 over 80 times x squared in SI units.
Let's move to part 5. Determine the time of flight of the box and the horizontal distance dE traveled on the ground. Let's start with the time of flight. The box reaches the ground at point D. Now, the ordinate of the point D is minus 100 meters because point D is 100 meters below the origin of the y-axis, which extends positively upwards. Now, we will use this equation. Replace y by minus 100 meters. Then, the time of flight is 4.47 seconds. Now, we want to calculate the horizontal distance dE. The horizontal distance dE is the abscissa of point D. So let's use this equation. And dE is the abscissa of the box at time 4.47 seconds. Then the distance is 20 times 4.47 seconds. Therefore, dE equals 89.4 meters.
Also, we have another method to determine the distance dE, using the equation of the trajectory proved before. Look at the figure. The ordinate of the point D is minus 100 meter. So replace y by minus 100, we get this equation. So x equals 89.4 meters, but the distance dE is equal to the abscissa of the point D. Therefore, dE equals 89.4 meters.
Let's move to part 6. Determine the position of the box when its speed becomes 25 meters per second. First, we are going to calculate the time needed by the box to attain a speed of 25 meters per second, and then we will find the expression of the position vector at this time. First, let's determine the expression of the speed of the box. This is the velocity of the box. We want the expression of the speed. The speed is the square root of Vx squared plus Vy squared. Square both sides of this equation. You will get V squared equals Vx squared plus Vy squared. Now, replace V by 25 meters per second, Vx by 20, and Vy by minus 10t. Therefore, the time needed by the box to attain a speed of 25 meters per second is 1.5 seconds. Now, replace t in the expression of the position vector by 1.5 seconds. You will get this equation. Then, the position vector of the box when its speed is 25 meters per second is 30i minus 11.25j. Its abscissa is 30 and its ordinate is minus 11.25.
Thank you for watching. If you like this video,
Subscribe to the channel, hit the like button and share.